So let's begin with the new topic, or the topic that is singular points of a differential equations. Now in earlier derivations or earlier lectures, we have seen one method that is called as separation of variables method for solving partial differential equation, or separating partial differential equation into that is ordinary differential equations in different variables. In that discussion, we have seen depending upon how many number of variables there are in a function, we have to go for this many number of differential equations. And while setting these type of differential equations, we have to set constants, and that constant depends upon how many number of variables are there. That means if there are 3 variables, then 2 constant. If there are 2 variables, there is 1 constant, and like that. So that is what an earlier analysis we have done. That is one method of solving the differential equations, partial differential equations, and solving method of one of the method. The second method which we are going to start today, not today, but maybe after 1 or 2 days after we finish this singular points, we are going to see we are going to solve different types of partial differential equations, namely Legendre differential equation, Lagrange differential equation, Hermite differential equation, and Bessel differential equation. These are very special basic type of differential equations. These equations we are going to solve by the method that is called as the series solution method. And as I said earlier, to understand the series solution method, or to test the series solution method, whether it is useful or not, or whether it is possible or not to get a solution of differential equation, partial differential equation, using this series solution method, first we have to test the singular point of differential equations. Now that singularity or singular points of differential equation plays a very vital role and important role in the usefulness of this method, that is the series solution method. So actually it is Frobenius series solution method. So whether this method is applicable or not, is to be applied or not, to be useful or not, that will be decided by this type of differential equations, this type of singularity. That means what type of singularity we do have. Actually we have learned all these things in the SYBST, as I said earlier. So a point can be ordinary, point can be regular singular, point can be irregular singular. Based upon that, there is one theorem, that is what type of solution you will get, that can be predicted based upon that, but that we will do somewhat later on. So today we will introduce the concept of singular point as follows. Okay, so let's start writing with me, because this is what, again, a theoretical discussion what we are going to do as follow. Okay, so let's consider let's begin with this. Let us consider, let me start. Yeah, consider the linear. Okay, we all know this terminology now. Consider the linear, then homogeneous second ordered differential equation of the type. Okay, so this is one very specific type we take for understanding purpose. It is y double dash, second differential of y with respect to x, plus some function of x, that is p of x, into y dash, plus another function of x, that is called as q of x, into y is equal to 0. So this is one prototype set type of differential equation has been given. Of this p of x and q of x are the functions of x. So x is independent variable, y is dependent variable, and we have written this second ordered linear homogeneous differential equation, of which we have to go for discuss its singularity. Okay, so where we know that where y double dash is d square y upon dx square, that is what, and y dash is nothing but first differential dy by dx. Okay, so let's go for testing the singularity. So let us discuss singularity. Before that, we'll discuss what do you mean by singularity. Let us discuss singularity of above differential equation of above differential equation, variable x is equal to some value x0. Now look at here. Now I am having this equation. Okay, so this equation is like this, something. So this p of x or whatever it is, like 1 upon x minus x0, and then y dash is equal to 0. This is what equation I am having. Now see here, when x takes value to be equal to x0, then this product, this particular bracket here, 1 upon x minus x0 will become 1 upon 0, and we know that 1 upon 0 is infinity. That means at this value of x, okay, x equal to x0, when this x and x0 becomes same, identical, then this term gets diverging, and whenever it diverges, goes towards infinity, and then there is writing this differential equation is totally meaningless. So in any of the differential equations there comes such terms where these terms, while taking that value of that variable to be exact value of that particular number, then some of the functions, some of the terms in that particular differential equation diverges, becomes infinity, and then our differential equation becomes meaningless. We will not be able to find out any solution of that differential equation. So we have to check, and such points are called as singular points, and the property is called as singularity. So whether any of the term in that differential equation diverges, becomes infinity at some of the value of the independent variable, these are to be decided, these are to be find out, and that is called as singularity. So testing singularity is one of the basic aspect before we go for this series solution method. That is what we are going to do here. Now there are certain conditions. First, actually there are 4 conditions. We know that if this function p of x and q of x, both these functions, both remain finite, okay, as x tends to x0. So when this variable x takes value this x0, both p of x and q of x remain finite, then the point x is equal to x0 is called an ordinary point, of given differential equation. This particular point is called as given differential equation. That means both p of x and q of x remain finite, they do not diverge. When I replace x by x0 in that differential equation, then this type of point is called as an ordinary point. That is first definition of first classification of the singularity. Now there is no singularity in this equation, therefore it is possible to get the solution for that differential equation. Second, if somehow if p of x or q of x, I am saying or, okay, p of x or q of x or both diverge means tends to infinity, diverge as x reaches or x is taken to be x0. So x tends to x0, either p of x or q of x or both diverges, then the point x is equal to x0 is called, now this is called as a singular point, singular point is called a singular point of given differential equation, So now when I put a value of x is equal to x0, either p of x or q of x or both becomes infinity. Whenever they become infinity, then there is no use of solving this differential equation. We won't get any solution for that differential equation, as any of the term in that differential equation becomes infinity. Whenever such situation occur, that point x is equal to x0 is called as a singular point, and whenever such situation occurs, this singular point can be classified in further 2 groups. Okay, there are 2 types of singularities. Okay, now let's see one by one. First is called as regular singular, and second is called as irregular singular. So type A, regular or non-essential. Regular or non, these two words are non-essential singularity, and we are going to define later on. Whenever such type of singularity exists, it is possible to get series solution of the given differential equation even though there appears a regular or irregular singularity. And the second type, as I said earlier, irregular or essential singularity. Irregular or essential singularity. Okay, and in such a case there is no method or series solution method is not applicable whenever there exists certain singularity for a given differential equation. Okay, now let's classify this or get the clear-cut definition of this first. Now a point, so which point is called as a regular singular and which point is called as a irregular singular? This classification, a point x is equal to x0 is said to be regular singular, is said to be a regular singular, is said to be a regular singular if either p of x or q of x, either of this, diverges means becomes infinity or tends to infinity, diverges at x tends to x0. Okay, that means when I put value of x, variable x equal to x0, either p of x or q of x diverges, but the product x minus x0 into p of x and x minus x0 square into q of x remain finite. Okay, so first condition is that either this p of x or q of x diverges when I put x is equal to x0, but in that equation if I write this, if I make certain changes, or if I multiply this p of x by x minus x0 and q of x by x minus x0 square, and then I find out, test its singularity whether it is finite or infinite, both of these terms remain finite, then such point at x equal to x0 is called as a regular singularity. Okay, remain finite as x tends to x0, the singularity in this case is a regular singularity. In this case is regular singularity. This is called as a regular singularity or non-essential singularity. And then B, second, the similar definition. A point x is equal to x0 is said to be an irregular singular. An irregular singular. This is said to be an irregular singular if p of x diverges faster than p of x diverges faster than 1 upon x minus x0, 1 upon x minus x0, so that x minus x0 into p of x. Okay, so this now look at this, x minus x0, when I put x equal to x0 or x0 is equal to x, so 1 upon x minus x is 0, so that becomes diverges. More than that, this p of x term diverges fastly, so this diverging is this, so it is approaching towards value of the limiting value to be infinity. So this is x and this is value p of x. So at particular value of x, this particular function diverges, that means becomes infinity. So such a point is said to be a diverging point, unlike this. So a function attains, p of x gets becomes more diverging as compared to 1 upon x minus x0. That is the condition here. X minus x0 into p of x tends to plus minus infinity, both this case, and or x minus x0 square into q of x, that also goes to plus minus infinity. That is also said to be diverges as x tends to x0. Okay, then such singularity called as irregular singularity. Then such singularity is called as irregular singularity. Irregular singularity. And note that this irregular singularity is not helpful at all. With such a situation, we will never get a series solution for that differential equation at that particular point of this irregular singularity. That this particular theorem we are going to test somewhat later on. Now see here what these particular things what we have written in a discussion, that can be understood if we go for very simple examples which are given in the solved section of our book. Okay, so let's go for one or two examples. Two examples we'll go for that. Example 1. Okay, so let's write the statement first. Show that the point x is equal to 0. Now this is my x0. 0 I am taken to be x0. X is equal to 0 is an ordinary point. Of Hermit's, this is the name of the scientist or mathematician who derived this equation, Hermit's differential equation. Form of this equation is y double dash minus twice xy dash plus twice lambda is equal to 0, where this lambda is some constant. Try to understand. This is the form of this Hermite differential equation. What is this? Y double dash minus twice xy dash plus twice y is equal to 0. This is the standard differential equation. Name of that differential equation is Hermite differential equation, and we have to prove that x is equal to 0 is an ordinary point of that differential equation. Okay, now let's go for the solution. One or two steps one can get the solution as follows. So the solution, so comparing Hermite differential equation with the standard form just now we have written. Okay, in above we have written this particular form, that is y double dash plus p of x into y dash plus q of x into y is equal to 0. So comparing Hermite differential equation with this standard differential equation, I'll get p of x is equal to minus twice x and q of x is equal to simply 2 lambda. This is simply 2 lambda. Okay, so q of x is 2 lambda. Actually this y should be there. This is the differential equation. Y double dash minus twice xy x into y prime or y dash plus twice y into lambda is equal to 0. This is Hermite differential equation. So compare this with the standard differential equation as we have taken from the beginning. So from that I can write p of x is equal to minus 2 of x and q of x is equal to 2 lambda. Okay, now so in the limit we have to take this limit x tends to x0, that is of p of x. This can be written as limit x tends to 0. I am taking this value to be x0 is equal to 0. Now if this p of x is obtained, it is minus 2 into x is equal to, now if I put this value of x is equal to 0 here, I'll get this is to be 0. So total value of this limit will be equal to 0 and this is finite. So this p of x, limit p of x at x tend limit x tend to x0 p of x, this takes a finite value. 0 is a finite value, 0 is not an infinite value. Similarly, second thing, limit x tends to 0 or x0 q of x. If this is calculated, I'll get limit x tends to 0. This is twice lambda, remains twice lambda only. There is no substitution needed. So this is also a constant or finite value. That means both at value of x is equal to 0, variable x takes value to be 0, then both p of x and q of x remains finite, even though I put value of x is equal to 0 in that equation or in both of these p of x and q of x function, and thus both p of x and q of x remain finite. Hence x is equal to x0 is an ordinary point of Hermite differential equation. This is an ordinary point of Hermite differential equation. Very simple example. In a single statement, we have written that x is equal to 0 is an ordinary point for Hermite differential equation. So we will come across this type of several types of application of this type of things when we go for actual series solution method. Okay. Then example 2. Show that, similar example, show that x is equal to 0 is a regular singular point, of Bessel differential equation. For that we must know the form of the Bessel differential equation, which is given by x square y double dash plus x into y dash plus x square minus n square into y is equal to 0, where this n is constant. Okay, so this is the standard form of Bessel differential equation. First we have seen Hermite differential equation, second is the Bessel differential equation, x square y double dash plus xy dash plus in the bracket x square minus n square into y is equal to 0. Okay, now we can rewrite. Let's go for the solution. Solution can be obtained like here. Solution, the Bessel differential equation. Bessel is another name of another mathematician. Bessel differential equation can be written as. So how can we write? Divide each and every term by x square. Then I'll get y double dash plus one of the x will get cancelled, so 1 upon x into y dash plus x square minus n square upon x square into y is equal to 0. So this Bessel differential equation has been rearranged by dividing each and every term by x square. I'll get y double dash plus 1 upon x into y dash plus in the bracket x square minus n square upon x square into y is equal to 0. Now let's compare this. Comparing it with this y double dash plus p of x into y dash plus q of x into y is equal to 0. We get, let's see what we get. What do we get? So I'll obtain p of x is equal to 1 upon x and q of x is also equal to x square minus n square upon x square. Okay, that is what one gets, p of x and q of x. And let's check here. Let at x is equal to 0, we are asked this x0 is to be taken to be 0, so this origin is to be taken. X is equal to 0, limit x tends to 0, this p of x is equal to limit x tends to 0, this is 1 upon x. So when I put value of x is equal to 0 here, 1 upon 0 becomes infinity, or that is called as diverges. So p of x itself diverges, or that becomes an infinite. infinite. Okay, so as per our condition, either p of x or q of x or both, if any one of them diverges, then this particular function x with this particular value x is equal to 0 is called as a singular point. Okay, so we'll write one statement here. Thus, when x tends to 0, p of x comma p of x diverges or becomes infinity, hence x is equal to 0 is called singular point, of Bessel differential equation. This is called as singular point of Bessel differential equation. And now let us decide its singularity. Let us decide type of singularity. Okay, this is what second step we have to follow. So let's go on calculating this. Let limit x tends to 0. Now here x minus x0 into p of x. Let's find out this. So limit x tends to 0. Now this is x minus 0 into p of x is, we have written x 1 upon x. So once this calculation is done, x minus 0 is x upon x is 1. So it becomes finite. So this p of x multiplied by x minus x0 in the limit x tends to 0, that becomes a finite. And second quantity we have to obtain, limit x tends to 0, x minus x0 into q of x square. Okay, x minus x0 into square into q of x. If it is obtained, this will give me limit x tends to 0. This is x minus 0 square into x square minus n square upon x square. So this becomes, okay, it is x minus 0 square is x square. So this x square in the numerator, x square in the denominator gets cancelled, and you will get this to be x square. So you will get limit x tends to 0, you will get x square minus n square. And as I know, when I put x is equal to 0, first term will become 0, but second term is minus n square. And as we said that n is certain constant, so this is also finite. And therefore, as per our knowledge, that x minus x0 into p of x as well as x minus x0 square into p of x both remain finite, both doesn't diverge, or they are not going to becoming infinity. That shows that this x is equal to 0 is a regular singular point of the this Bessel differential equation. Okay, so right here, thus x minus x0 into p of x and x minus x0 square into q of x both remain finite. Hence x is equal to 0 is a regular singular point of Bessel differential equation. Okay, now there can be several other types of problems are there. I think it is not necessary to go for all such problems. There are many problems. We can go for this. Okay, or I think we'll go one irregular singularity. That problem will take, and then maybe stop here. Okay, example 3. So you can carry out this. Example 3. Show that the point, again x is equal to 0, is an irregular singular point of differential equation. Now this is the differential equation given: x square into x minus 2 square into d square y upon dx square plus 2 into x minus 2 into dy by dx plus x plus 3 into y is equal to 0. Now this is any differential equation. This is not any standard form of differential equation. Okay, now we have to test, or we have to find out that x is equal to 0 becomes an irregular singular point for this. Now solution. So we can rearrange this given differential equation in what form? We have to get in the standardized form. So for that we have to divide this by x square upon x minus 2 square. Okay, so we have to divide this entire equation. So right here, dividing entire equation by x square into x minus 2 square, we get, let's see what we get. So if I divide this, left hand side of this first term will be simply d square y upon dx square, plus one of this x minus 2 gets cancelled, so it is 2 into x square upon x minus 1 into dy upon dx. Okay, so what is this? This is 2 upon, no, we are dividing this, so this x square will come in the denominator, 2 upon x square into x minus 1 or x minus 2, this is 2 here, or shall I write? I'll write once again. I'll write once again. So this gives me okay, I am dividing this by x square upon x minus 2 square, so one of these get cancelled, so 2 upon x square into x minus 2 into dy upon dx, plus this is x plus 3 upon x square into x minus 2 square into y is equal to 0. Call this to be equation 1. Now we can compare this, so comparing it with, so comparing equation 1 with, this is our y double dash plus p of x into y dash plus q of x into y is equal to 0. So when I go for this calculation or this comparison, I'll get p of x is equal to simply 2 upon x square into x minus 2 and q of x is equal to x plus 3 upon x square into x minus 2 square. Okay, now when what will happen, we have to test the limit x tends to 0, that is this x0 takes value to be 0, this p of x. So let's check what happens to this. Limit x tends to 0, this is 2 upon 0 into 0 minus 2, so this is 2 upon 0 and that becomes infinity, or that is infinite. That means p of x diverges when I put x is equal to 0 there. Similarly, limit x tends to 0, this q of x, if it is written there, it also limit x tends to 0, that gives you x plus 3 upon x square into x minus 2 square. So this is again 0 plus 3 is 3 upon 0 into 0 minus 2. So again anything upon 0 is again equal to infinity, that is this is also infinite. So both of them diverges, both of this p of x as well as q of x diverges. Okay, therefore we can conclude that thus as x tends to 0, both p of x and q of x diverges, hence x is equal to 0 is a singular point of given differential equation. Okay, and now let's test its singularity. Let's test singularity. Okay, anyone has any doubt? Let's test the singularity, and for that we have to go for this test. Limit x tends to 0, Now x minus x0 into p of x. Already we have found out p of x. So this becomes limit x tends to 0. Now it is simply x0 is 0, and p of x is this 2 upon x square into x minus 2. So what happens there? One of these x gets cancelled, so it is 1 upon x remains there, so it becomes 2 upon x into x minus 2, and when this x becomes 0, this again becomes infinity, so this is also infinite. So this limit x minus x0 into p of x also diverges or becomes infinity when we put value of x0 is or value of x is equal to 0. That is point. And similarly, limit x tends to 0 x minus x0 square into q of x, if it is tested or find out, limit x tends to 0, this is x minus 0 square. And now next point here, it is we are having this what is this? This is q of x. Q of x is x plus 3 upon, this is x square into x minus 2 square. Just calculate this. So this gives me limit x tends to 0. Now this is x square, this is x square, so that cancels, and I'll get x plus 3 upon x minus 2 square. So when I put value of x is equal to 0, that will give me 3 upon 2 square, so that is going to be 3 upon 4, and that is finite. So that becomes 3 by 4 is finite, and that's what as per our condition. Okay, I need to have x minus x0 into p of x is equal to finite, as well as x minus x0 square into p of x is also to be finite. Then and then this given point is called as a regular singular point. But here in this case, second, x minus x0 square into p of x remains finite, but x minus x0 into p of x, okay, we are not supposed to AND, or we are just saying or. Either of this becomes an infinite, then such point is said to be an irregular singular point. Okay, so right here, as x minus x0 into x minus x0 into p of x tends to infinity as x tends to 0. Hence, okay, even though this becomes finite, this becomes infinite. Both of these are supposed to be remain finite. Then and then it is called as a regular singular point. At this stage, in this particular problem, first quantity x minus x0 into p of x, x tends to infinity as x tends to 0. Hence, x is equal to 0 is called an irregular singularity. Irregular singularity of given differential equation. So these three problems may make you clear how to go for calculation of the singularity of a given differential equation. Now along with that, there is one small derivation is remaining. We are not going to cover everything here, so I am just going to mention what is the how to test singularity at infinity. Okay, so next part here, singular point at infinity. Singular point at infinity. That is infinity. Now we have to go for a method for that. Exactly similar method is obtained here. Okay, it's to be obtained here, and so x tends to infinity. Earlier we have said x is equal to 0, and earlier problems we have shown x is equal to 0. What happens in the first problem, second problem, third problem, etc. When I put x is equal to infinity in my given differential equation, then okay, so when we are supposed to find out this, the differential equation y double dash plus p of x into y dash plus q of x into y is equal to 0 requires a special technique in which the differential equation y double dash plus p of x into y dash plus q of x into y is equal to 0 is transformed. Okay, this transformation transformed into another equation z double dash plus p of z into z dash, sorry, p dash, okay, let's call this p dash z into z dash plus q dash into z is equal to 0 with the help of transformation, transformation. What is that transformation we have to use? Z is equal to 1 upon x. So right here, when I put x is equal to 0, this z becomes infinity. So my differential equation is given is this. So here when I put x is equal to 0, before that what I have to do? Convert this differential equation into the new form with this transformation z is equal to 1 upon x. So whatever equation I am getting here, this test its singularity at x is equal to z is equal to 0, means we are testing singularity of this differential equation at x is equal to infinity. Once again, let's see what I am saying. So this is my original differential equation given. Now transform it into this equation with the help of this transformation. So I'll get this. Test its singularity for x is equal to 0 means, test singularity of this differential equation for z is equal to 0 means, when I have z is equal to 0, this means x is equal to infinity. So if what I am testing singularity of this for this equation for z is equal to 0 means I am testing singularity of this equation for x is equal to infinity. That way we have to go for this singularity, and in this transformation equation, now all these things are given there in textbook. You can look all these things later on. Actually I am not going to give all these things, but this transformation equations gives me something very special, and these are two terms. So that is this p dash of z is obtained to be twice z cube minus z square into p of 1 by z, p of 1 upon z divided by z raised to 4th, and q dash of z, this second coefficient is obtained to be q of 1 upon z divided by z raised to 4th. Okay, so see here I am showing this is not that easy to directly go from this transformation equation to get this transformation and get this. So for that there is at least one page entire derivation is there. Look this derivation on page number 3.22. If you get some book later on, you will get this to be page number 3.22. Everything is given. This is not that difficult. So here we have to test for this, for these coefficients, test singularity at z is equal to 0 means we are testing singularity of earlier given differential equation for x is equal to infinity. So same thing what we are going to do here. Again there also we will have ordinary point. That means if z is at z equal to some number, some z is equal to some number, or z is 0, this p of p dash z as well as q dash z. Okay, so for z is equal to z0, or I'm saying 0. Okay, let's take this to be 0. Z is equal to 0. This p dash of z and q dash of z remain finite. Then this z is equal to 0 is, this is called as ordinary point. Then second is, this is first point, ordinary point. Second is either p of x or tends to infinity, sorry, in spite of that I should write this p dash of z or q dash of z, okay, or this or both diverge, that means becomes infinity at z is equal to 0, then such is called as a singular point. Then it is called as singular point, just like what we did in earlier case. This is called as singular point. And third case, when this z minus z0 into p dash of z or z minus z0 square into q dash of z, okay, either of this or this tends towards infinity, then okay, that means if this they become finite, okay, they become finite, then z is equal to 0 is called as regular singular, or in other words I'll say that x equal to infinity is a regular singular point of the given differential equation, y double dash plus p of x into y plus y dash plus q of x into y is equal to 0, म्हणजे त्याचा तो रेग्युलर सिंग्युलर पॉइंट आहे. जर z इक्वल टू 0 ऑफ दिस, म्हणजे ह्या डिफरन्शियल इक्वेशनचा जर तो रेग्युलर सिंग्युलर पॉइंट झाला तर x is equal to infinity is a regular singular point of our earlier given differential equation. And last fourth case, as I said earlier, when in this case this z minus z0 into p dash of z or z minus z0 square into q dash of z, either of this diverges, any one of this or both diverges, then z is equal to 0 is an irregular singular point, and therefore x is equal to infinity is an irregular singular point of this. Okay, so I am sure this is bit more mathematical, requires some derivations and lot many things, but here don't try to go into details of that, not needed. Only we have to just go for understanding that as we calculate at singularity at x equal to 0 for any differential equation, similarly we can calculate singularity for x is equal to infinity for any given differential equation. For that we have to go for these transformations, then we have to go for this p dash of z, q dash of z, and we have to rewrite these conditions again, and then we can go for calculation of this. So such type of some numerical example is also given in your textbook, you can check it later on, but this is not needed at this stage. Okay, so today we will stop here as we have almost completed 50 minutes. I'll stop here. In the next lecture we are going to start the solution of differential equation using the series solution method. Very interesting and not that easy, but important and interesting method we are going to discuss, we are going to study, because these things we have never learned earlier. So what is my series, why we have to assume is a series solution, what are the conditions, then depending upon singular point what type of different types of solutions are possible, etc., etc. These complicated things we are going to discuss in next lecture onward or tomorrow onward. Tomorrow we are having 2 lectures, so at that time we'll start this series solution method. There is one first theorem. Based upon this first theorem we are going to understand first method. जसं आपण सेपरेशन ऑफ व्हेरिएबल्स मध्ये पहिल्यांदा एक छोटीशी मेथड डिफाइन केली, and then we applied this method for different types of differential equation. Here also we are going to understand the method or the that is called as syntax or the logic, or just what we draw a flow diagram in C programming. Here also we can draw a flow diagram for this type, solving this type of problem. And once we understand this methodology, it can be applied for any differential equation or standard differential equation. Basically in this exercise we are going to solve Legendre differential equation, Laguerre differential equation, Hermite differential equation, and Bessel differential equation. Of course these equations are very fundamental and important equations in physics, not in mathematics. Mathematics मध्ये त्याचा यूज आहेच, त्याच्यापेक्षा जास्त यूज या 4 differential equations it is most useful in the physics, and that's why we are going to concentrate on this type of 4 differential equations and their solutions. That will be done in the next lecture. Okay, so today we'll stop here, and let me take the attendance. Okay, all you are there? Yes, all 7 people are there. So let me take attendance and then you can stop. Okay, so Gavandi, Borshe, Padtare, Vedasri, Purva, Pratidnya, Aira, and this Vishal. Okay, let me take this attendance. See, this type of file is generated. Okay, now I am just calling this to be ty attendance. Okay, ty class list. This is the date comes 13/10/2020. I can show you here how this file looks to me. just check this file. A clear cut attendance comes here, and that shows it following.